Hey everyone. Ever stop to think about the invisible world that makes our entire digital life possible? We're talking about that hidden infrastructure that carries everything from our texts to our favorite shows. We are talking about communication channels.
Seriously, just think about it for a second. How is this explainer traveling from our servers, zipping through the internet, and showing up on your screen right now? The answer is a whole series of incredibly complex but really elegant communication channels. And by the end of this, you'll know exactly how that works. So here's what we're going to cover. We'll start with the basics. What even is a channel? Then we'll see where they're hiding in plain sight. After that, we'll get into how engineers actually model them, how to measure their performance, and finally, what happens when you get a whole crowd of them working together.
All right, let's dive right in and start answering that big question. The entire journey of how this all works begins with understanding this one fundamental idea: the channel.
So, at its core, a communication channel is just the road that information travels on. It can be something you can physically touch, like a fiber optic cable, or it can be something totally invisible, like a radio frequency. But the main thing to remember is that it's the pathway connecting a sender, in this case our server, to a receiver, which is you.
And these pathways, they're not just for the internet. They are literally everywhere, woven into the fabric of our daily lives in ways you might not even realize. Let's look at a few examples hiding in plain sight.
Your home Wi-Fi is a perfect example. It carves up the 2.4 gigahertz radio band into 13 smaller channels, kind of like separate lanes on a highway. That's how it keeps your laptop's traffic from colliding with your phones.
Or how about this? Remember flipping through TV channels? Each one of those, like the old Channel 2, was its own dedicated 6 megahertz wide channel. Now with digital TV, those same physical channels get cleverly split into multiple sub-channels. That's why you see things like 2.1, 2.2, and so on.
This is also super critical for safety. Marine radios use 88 distinct channels to organize all the communication out at sea, with the incredibly important Channel 16 universally reserved for distress calls. It's a channel that literally saves lives.
Now this one's really cool because it kind of expands the whole definition. A channel doesn't just have to cross distance, it can also cross time. When you save a file to a hard drive, you're basically using it as a channel to send a message from your present self to your future self. Pretty wild, right?
So if these channels are everywhere, how on earth do we design and build them, especially the invisible ones? Well, we have to model them. We create a kind of blueprint that describes how a signal is going to behave as it travels through the channel.
There are really two main ways to go about it. A physical model tries to be perfectly accurate by calculating every single reflection and interaction a radio wave has with its environment. As you can imagine, that gets incredibly complex really fast. So, more often, engineers use a statistical model. It uses probability to predict the channel's behavior based on past measurements, which is just way more practical for building real-world stuff. We can also break these models down by the type of signal they're for. Digital models for things like your internet are all about bits and bytes, how many are getting through and how many have errors. On the other hand, analog models for something like old-school radio focus on the continuous wave itself, how much static or noise is getting in the way and distorting that signal. And this brings us to a question we have all asked all the time. Why is my connection so slow today? The answer is all about how we measure a channel's performance. And believe me, it's not just about speed. There are a few key metrics that tell the whole story. And this illustrates the four main ones perfectly. Bandwidth is basically the size of the pipe. A bigger pipe means more data can flow at once. The bit error rate tells you how often a 1 gets accidentally flipped to a 0, which causes those glitches. Latency is simply the delay, how long it takes for your data to make the whole trip. And finally, the signal-to-noise ratio measures how clear your signal is compared to all the background static. A really good connection needs to score well on all four.
Okay, so far we've mostly talked about simple one-to-one channels, but the real world is a crowded place. So let's look at what happens when multiple users all need to share the same medium, like in a cellular network.
First up, you have a broadcast channel. This is one-to-many. Think of a single cell tower sending data down to all the different phones in its area. One sender, many receivers. Simple enough. The reverse of that is called a multiple access channel. This is many to one. It's the uplink. That's when all those different phones need to send data back to that one cell tower. This takes a ton of careful coordination to make sure they don't all talk over each other. And that brings us to the biggest challenge of all, interference. This happens when you've got multiple, separate conversations happening in the same space. Two different cell towers, for instance, might be talking to their phones, but their signals can bleed over and interfere with each other. It's really just like trying to have a conversation in a super noisy, crowded room.
So from a simple wire to a complex global network, communication channels really are the unsung heroes of our connected age. They carry our data across continents and, as we saw, even across time. And as our world demands more data, more speed, and more connections, figuring out how we manage these invisible pathways is what will define our future. So as we keep packing more signals into an already crowded world, that leaves us with a big question. What will the next great communication channel look like?